Okay, now we're ready to talk about what it means to be a basis in this new context. We've talked about what it means to be a basis before, but first of all, we were only in the real numbers Rn, the real number vectors Rn. Here, we're going to be talking about what it means to be a basis in some other vector space, or potentially some other vector space, and more importantly, what it means to be a basis of a subspace. So let's take a look, first of all, just to remind ourselves what the definition of a basis is. If you have a subset S of some vector space V, then that subset S is called a basis of V if S is linearly independent and S is a spanning set of V. Those are the two criteria that have to be met. Remember that if you have an n-dimensional vector space, like Rn, for example, and you have k vectors in a subset, if k is less than n, if you have fewer vectors in your subset than there are dimensions, that's not enough vectors to span the set. So this is going to be true of a subspace as well. This is why we need to have a spanning set of V before we can call it a basis. If you have too many vectors, if you have more than n vectors in your subset, if k is greater than V, then one or more of those vectors can be written as a linear combination of the other. So they're not linearly independent. So you need to have k be exactly equal to n before you can talk about the members of the subset being a spanning set for V, and having them linearly independent means that you don't have too many. Making it a spanning set means you don't have too few. Let's take a look at an example. I've got a set here called S, which I'm claiming is my subset of the polynomials of degree 2 or less. And the set S is made up of some polynomials of degree 2 or less. This one, and this one. And notice that I've got one of each degree. One of degree 2, one of degree 1, and one of degree 0. This is 1 times x to the 0 power. I want to find out if S, this set right here, is a basis for P2. It has to meet the following criteria. S has to be a subset of P2. S has to be linearly independent. And S has to span P2. If all three of those requirements are met, then we can say S is a basis for P2. So let's check each of these criteria to see if S is a subspace of P2. First one is that S is a subset of P2. That means that every element in S is also in P2. Well, P2 is just the set of all polynomials of degree 2 or less. If each one of these is a polynomial of degree 2 or less, then this criteria is met, and that is in fact the case. So now we move to the next criteria that has to be met. We need to find out if S is linearly independent. And if you will remember, one way to check for linear independence is whether a linear combination of the vectors in a space, if that linear combination equals 0 and it has only the trivial solution, then those vectors are linearly independent. So if we find a linear combination of these vectors, let's write one out. Let's say, let A, B, and C be in the real numbers. I can do this because I'm scaling vectors in a vector space, and I haven't been told otherwise, so that means that my scalars are coming from the real numbers. Let A, B, and C be in the real numbers, and then I can write a linear combination of my vectors v1, v2, and v3, where that's v1, that's v2, and that's v3, is a times x squared plus 1 plus b times x plus 1. Let me spread that out just a little bit better. A times x squared plus 1 plus b times x plus 1 plus c times 1 equals 0. But what does 0 look like in this in P2, right? P2 is a collection of polynomials. So that means that this zero vector in that space is going to look like this: 0x squared plus 0x plus 0. And that's handy because now I'm going to expand this side here, collect like terms, and then I'm going to compare it to the right-hand side here. Let's do that distribution. I get ax squared plus a plus bx plus b plus c equals 0x squared plus 0x plus 0. And that gives me ax squared plus bx plus this collection of constants a plus b plus c equals 0x squared plus 0x plus 0. And then by comparing the coefficient of, let me change to a different line, the coefficient of x squared on both sides, it's clear that a has to equal 0. And then I'll compare the coefficient of x on both sides, and it's clear that b has to equal 0. And lastly, I have a comparison of, the right pen, the coefficient of x to the 0 power on both sides, and that gives me that a plus b plus c equals 0, but I already know that a and b are 0, so that tells me I wrote a 0 where I meant to write a c. The muscle memory is very similar. So that means that c also equals 0. So I have then a solution, and in fact the only solution to this problem. What are a, b, and c? They have to be 0. Therefore, this is the trivial solution. It's the only solution, and that tells me that the vectors in that space are linearly independent. Now, lastly, do these three vectors span the space of P2? Well, we have the right number of vectors. We don't have too many, we don't have too few. If we only had 2 here, remember polynomials have one more vector in their space than this subscript suggests. So I need 3 vectors in the space to span P2. If I had any more, then the 4 or more vectors in here would not be linearly independent. If I had any fewer, it wouldn't be enough to span the entire space. So I have the right number, but do they in fact span? I might have, for example, 2 vectors that kind of point in the same direction, and then a third vector, and that wouldn't span all of the space. Well, because they're linearly independent, they also span the space. So that criteria is also met, and we have that this collection of polynomials, x squared plus 1, x plus 1, and 1, together are a basis for P2. Now, there are many other possible bases for P2, and this is not even the standard basis. The standard basis would be this, oh, wrong pen. The standard basis for P2 would be x squared comma x comma 1, where I don't have any additional, necessarily any additional constant terms here. I just kind of picked this one because it was a little different. And also because I wanted to point out that there are multiple bases for the same space. If you do the same criteria check on these 3 vectors, you'll find that they form a subset of P2, they are linearly independent, and they span P2. So this is also a basis. And in fact, there are no extra coefficients or things hanging on here, so this is the standard basis for P2. This is equivalent to saying that the standard basis for R3 is the vectors 1, 0, 0, it's a collection of vectors, 0, 1, 0, and 0, 0, 1. Right, that's the standard basis for R3. The standard basis for, let's see, M 2 by 2 is the collection of matrices. These are 2 by 2 matrices. There are going to be 4 of them. And they are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. there's sort of a unit in each position. Right here I've got a unit in each position, uh, row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. Here, and these are matrices, right? Here I have real number vectors, so I have uh, a unit in each of the 3 positions in an R3 vector. Here I have a unit in each of the powers. Right here I have power of 2, that's a single polynomial with a coefficient of 1 and no extra terms on it. That's like a unit in P2 where the power of the variable is 2. Here's a unit where the power of the variable is 1, and here's one where the power of the variable is 0. So that's effectively what we're looking at with a standard basis. But my point with this exercise was to show you that uh, something else can be a basis, and this is how you determine whether it is or not. You have to confirm all three of these features.